Okay, so section 7.1 is the roots and radical expressions. Definition in the book says if a to the n power equals b, then a is called an nth root of b. So a couple examples here. If you've got 2 to the fourth equals 16, uh, and then you also can take negative 2 to the fourth, and that equals 16, then you know that, so 2 and negative 2 are fourth roots of 16. Fourth roots of 16. So you could do that with all kinds of different things, whether they're odd roots or even roots. Um, which brings us to trying to understand what's going on between the odds and the even powering functions. You're used to y equals x and y equals x squared, maybe even y equals x cubed. But all of the odd powering functions like y equals x, x to the third, x to the fifth, x to the seventh, all of them follow the same format right here. They have this general looking shape with some minor differences. They get sharper and steeper on the sides, and then they come into uh, the origin and then come out the other side kind of flat and then get real steep again. The even ones look like a parabola, and as you increase the power, like to x to the fourth and x to the sixth and x to the eighth, you start getting sharper corners and steeper sides. Well, what happens if I would take y equals 5 and intersect it with this graph? The question is, how many times do they intersect? Um, or how many solutions would there be to something like this? X to the third equals 5. The answer is only one solution. Now, I'm not promising that would be a very nice one, but it definitely would only be one solution. Likewise, y equals 0, right through there, crosses at the origin one time. It's as if we're trying to solve something like this. Only one solution. So we had one solution on this particular situation, and also one solution on this particular situation. Now, what happens if we had y equals negative 3? So in other words, we're solving an equation x to the third equals negative 3. That, well, that is also a possibility. There's one solution to that particular situation as well. So, um, in the odd powering function case, there is always one solution. Always. Now, jump over to the even case. Same idea. Y equals 5. So we're talking about something like x to the fourth equals 5. Well, that happens in two spots. So that has two solutions. Y equals 0, the good old x-axis. X to the fourth equals 0. Well, that happens to cross one time, right there at the bottom. What about y equals negative 3? So we're talking about x to the fourth equals negative 3. There are 0 solutions. Maybe I should write the word no solutions to this. As you can see, the line doesn't cross the graph at all. So there's a nice chart in the book which kind of shows you, talks about this particular situation. Okay, now I want to bring up the point that these two questions at the top of the screen are not the same. The square root of 25 is not the same thing as solving an equation x squared equals 25. Solving an equation like this is saying find all solutions. Every x value which makes this true. Now I do realize that I'm going to be taking a square root of both sides. Why does that look so... Oh. I had to figure out what was going wrong with the camera. It looked all blue. I think I fixed it. All right. Um, in this particular situation, when you do this, there are two possible answers. There's the positive and negative 5. Both of them will cause x, when you square it, to become 25. So you have two solutions. This one is a different question. This is asking for the positive square root of 25. And the answer to that is just plain 5, where the answer to the other one was plus and minus 5. So two completely different questions. Now, these particular questions in the book, it says find all real roots, and they say find all the real cube roots of 0.008 and negative 1,000 and 1 over 27. Well, so I've modified the question a little bit, but it says exactly the same thing, right? So to solve this, you would take the cube root of both sides. And when you type the cube root of 0.008 on your calculator, make sure you can do that. You're going to type the 3. You're going to find something that looks like the xth root. And then you're going to type 0.008 and then equals. Okay? When you do that on your calculator, you should probably get 0.2. Alright, same thing's going true on this other one, or is true for this other one. You're taking the cube root of these, and when you take the cube root of negative 1,000, you get negative 10. Notice that each time I'm doing this, for the odd roots, I'm only coming up with one answer, which goes along with what we just said a few minutes ago. Cube root, cube root. Now, what's the cube root of 1? Well, that's 1. What's the cube root of 27? Well, that's 3. There's your answer. Now we jump to the even powers, and so now we're doing a fourth root. We're finding all the possible solutions to this, and there are 2, right? Positive and negative 1. The fourth root of 1 is still 1, but you can consider the positive case and the negative case, just like we talked about in that other graph that we showed a few minutes ago. All right, so I can take the fourth root of this one, right? Nope, this is the one where it's below the x-axis, so there's no solutions to this. What about this one? Taking the fourth root of both sides. Fourth root. X equals plus and minus, right? Because you're taking an even root of a positive number in a solving situation. We've got the fourth root of 16, that's a 2, and the fourth root of 81, that's a 3. Just a couple examples there that you can use. Okay, next, example 2. Example 2 deals with various roots, and we take the cube root of negative 8. We can all do that, right? Because you can take the cube root of a negative number. The graph we showed earlier said there would be one solution. The cube root of negative 8, a nice integer, negative 2. How about the square root of negative 100? No real solution to that. I know, several of you are going to say, well, what about 10i? That's true, but keep in mind, in this chapter, the question is about real solutions. What are the real solutions? That question does not apply to this particular situation because there are no real solutions. I know 10i is a solution, but that is an imaginary result. Okay, it's in that imaginary number category. The fourth root of 81. Well, what number to the fourth power gives me 81? 3. Right? 3 to the fourth is 81. The next property that the book talks about or shows you is it says for all negative numbers, when you take the nth root of a to the n power, then you get the absolute value of a. where n is even. Now, if I were to kind of summarize this, there's three things I would say to you. First of all, please notice that you're dealing with an even root. An even root. And when you get done, you get an odd power in your answer. An odd power in your answer, whether it's a 1 or a 3 or a 5 or 7, doesn't really matter. Then, if you've got an even root and an odd power in your answer, and both things have to be true, you have to put absolute value bars around that particular variable. So let's take a look at a couple examples. So the square root of 4x to the 6th. All right, now I'm always going to talk about things like perfect squares and leftovers, or perfect cubes and leftovers, but none of these examples are like those. So when we get down the road and you hear me say that, it'll make more sense. Because these are perfect squares. We do know the square root of 4. We can figure out the square root of x to the 6th. Something times itself gives me 4. Well, everybody's going to say 2. What times itself gives me x to the 6th? X to the 3rd. Okay, folks, we had an even power, we are even root, and we ended up with an odd power in my answer. Therefore, I need absolute value bars around the x to the 3rd. Look at that next example. So we have the cube root of a to the 3rd. Well, that's simply a. The cube root of b to the 6th. Well, 3 goes into 6 2 times. Okay. Did we start with an even root? Nope. Therefore, no absolute value bars. We're done. Okay. On the next one, we've got the 4th root of x to the 4th, y to the 8th. So, 4 divided by 4, x to the 1st. 8 divided by 4, y to the 2nd. Did we start with an even root? Yes. Did we end up with an odd power in our answer? Only here, so I only need absolute value bars around that one, not the whole thing. Last example here we have. Ooh. In the book, let me read this example a little bit so it makes a little bit more sense. It says a citrus grower wants to ship a select grade of oranges that weigh from 8 to 9 ounces in gift cartons. Each carton will hold 3 dozen oranges in layers of 3 oranges by 4 oranges. The weight of an orange is related to its diameter by the formula W equals D to the 3rd over 4, right there. Where D is the diameter in inches and W is the weight in ounces. Cartons can be ordered in whole inch dimensions. What size cartons should the grower order? Well, we know that we want the weight of this thing to be between 8 and 9 pounds. Weight is equal to diameter cubed over 4. So we're going to substitute in there. Now we need to go through the process of solving it. We're going to multiply by 4, multiply by 4, multiply by 4. So we have 32 is less than or equal to d to the 3rd, which is less than or equal to 36. Now what? Well, if I need to take the cube root in the middle, I'm going to have to take the cube root there and the cube root there, and they're not going to be pretty numbers. This one's 3.17. And that one over there is 3.3. So the diameter of the orange that we're looking for is between 3.17 and 3.3. And that's it for section 7.1 notes.